Welcome back to multivariate calculus. In this video, we want to look at the divergence theorem. The divergence theorem is actually two separate theorems. One of them is a simple corollary to Green's theorem. I say simple, the derivation is a little bit cumbersome. It involves arc length parameterization, which hopefully you remember from a much earlier video, is never exactly fun, but incredibly useful. Once we have that, which is sometimes called the two-dimensional divergence theorem, we're going to extend that idea out into 3 dimensions and create the three-dimensional divergence theorem, which is eventually going to take surface integrals and relate them to volume integrals, the same way that Green's theorem and Stokes's theorem relate path integrals to area integrals or parametric area integrals. All right, so without further ado, let me get my head out of the way and let's start in with a reminder that Green's theorem tells us that the closed integral on a closed path C of f dot dr is equal to double integral on R of partial g partial x minus partial f partial y dA for our vector field F having components little f, little g. And as I warned you, I'm going to assume that I have an arc length parameterization, R of S equals X of S, Y of S. I forgot some words in here. This is an arc length parameterization for the curve, which forms the boundary of the region we care about. Now, if I think about that curve, and I think about an arbitrary point here, I know that I can get the tangent vector as R prime of S, which is going to have components of X prime of S and Y prime of S. And then because I'm in the two-dimensional plane, finding a normal vector is pretty straightforward. The vector normal to this is going to have components that are the same X and Y, but flopped, and a negative gets introduced somewhere. All right, so looking at the picture here, it looks like my tangent vector had positive X component, positive Y component. My normal vector is going to still have positive X component, but it has a negative Y component. And again, just the magnitudes of X and Y get switched between the tangent vector and the normal vector. That's the same idea that leads you to two perpendicular lines have opposite reciprocal slopes. All right. Now I want to consider integrating over this same curve, but instead of taking the component along the curve, I want to take that component perpendicular to the curve. So I'm going to take F and I'm going to dot it with N ds. Performing that dot product is fairly straightforward. F has components of F and G, N has components of Y prime and X prime. So we're looking at the integral over our curve C of little f times x or times y prime, which I'm going to write as dy ds. It would be plus, but there's a negative here on this component, so we're going to have minus g times dx ds, and the whole thing ds. Then if I distribute that ds, it will cancel out these ds's in the denominator. As I've said before, technically speaking, that's not how derivatives work, but it gives us the right answer, so we kind of just close our eyes and pretend and hope for the best. And most of the time it works out, so we're happy that we don't have to go through 3 pages of validating for ourselves that yes, it will work in this case. But that's just going to give me f dy minus g dx. And at this point, I can do something that might seem a little bit strange, and I can factor that into a dot product of a vector with components of minus g then f, and get back to my usual dr with components dx and dy. Right, again, the big idea here is that dr has components of dx and dy. And then the next step is the doozy. In the next step, I'm going to go back to Green's theorem. Green's theorem says that if I have an integral, a line integral of a vector field over a closed curve, that's the same thing as the area integral over the region inside the curve of the partial of the y component, which in this case is f, with respect to x, minus the partial of the x component, which is minus g. So minus a minus is plus partial g, partial y, dA. All right, just bringing the left-hand side back down, that was the integral over c of f dot n ds equals this. And this thing is called the two-dimensional divergence theorem. All right, so now that we've gone through the math, what is it that we were actually calculating? We had our closed loop. And again, instead of taking the derivative along the loop, we're instead looking at this time at the component of the vector field that goes through the loop. How much is the vector field spreading out, coming out from this loop, or how much is it contracting in, coming inward through that loop? We call that idea divergence. Specifically, this bit that came into the integral behind me is the divergence. And if you look at that, that kind of looks familiar. Taking a derivative with respect to x, taking a derivative with respect to y. And so if I expand out to 3 dimensions, instead of just partial of f with respect to x and partial of g with respect to y, I guess I'm going to want partial of f with respect to x, partial of g with respect to y, and partial of h with respect to z. That seems like a natural way to expand this out into 3 dimensions. We'll call that the divergence of f, since it's the divergence theorem. And you should convince yourself that this is exactly what happens if you take the dot product of our del operator and our vector field. All right, so with that idea in mind, I want to expand out to a three-dimensional divergence theorem. And again, I just want to think about this rather than trying to dive into actually using the math to perform integration, because the real value of the divergence theorem is in the geometry of vector fields. If we have a vector field, and instead of just thinking about it in the plane and thinking about that closed loop, I want to think about a vector field in 3 dimensions that's free to go in any different direction. In order to enclose this vector field, instead of a flat curve, we need a solid surface. And so we're going to take the double integral over a closed surface of f dot ds. And that's convenient. Remember that ds as a vector points outward from the surface. It's a normal vector, which is exactly what we had in the first divergence theorem up here. When we had the divergence version of Green's theorem, we wanted f dot n, the component of f, normal to the curve. And when we defined a surface integral, that's how we defined it. Vector s is normal to the surface. But then the right-hand side should turn out exactly how we expect it to. It's going to be the integral over the stuff enclosed in the surface of the divergence of that vector field. And for a volume integral, again, this gives us a very interesting idea. You don't have to take the time to look inside everything that's happening in a region. You can just get the picture of the surface. Or alternately, the picture on the surface tells you everything that's happening in the region. Finally, here at the end, we get to the whole point of everything. You may have heard at some point in the past that Isaac Newton invented calculus in order to understand his law of universal gravitation. Very specifically, what Isaac Newton needed was to convince himself that instead of having to think about the entire mass of, say, planet Earth, when you're thinking about the gravity happening on the surface, you can treat the mass as being the entire mass at a point on the center of the Earth. And that's what the divergence theorem tells us. If you are on the surface, whatever is coming out through that surface gives you the same result no matter what it looks like inside, right? If what comes through the surface looks the same, it doesn't matter what's inside, it all works the same. And so by knowing that this point mass gives you the same behavior on the surface as trying to think of the Earth as a large object, it greatly simplifies calculations in mechanics, and that's what calculus is all about. I've got one last task for you for my entire lecture on calculus, and that's going to be to look at what this does to a potential function, to a conservative vector field. All right. So consider a conservative vector field, a vector field f defined by a potential function phi and the gradient of that. I would like you to calculate the divergence of this vector field. Take a couple of minutes to work through the algebra there, see what you end up with, and I'll see you in the last video.